Hello and welcome to the continuing videos in our linear algebra series. So in this video we're going to be talking about probably the introduction into vectors. And so vectors are probably objects you might have seen, especially if you've done any kind of physics back in high school or maybe even in university or something like that. Vectors are an object that has kind of two main properties. So whenever we're talking about a vector, usually it looks something like this. There's two main things that we have about that vector. We have its length. We call it the vector v. We have its length, sometimes referred to as its magnitude. Often we can write that as the length of the vector. Unfortunately, length has two different things. So in following along here, as I'm going along with the text that's currently being used, granted, I have seen, so it's possible, depending on what resource you're using this term, or just looking things up, it might just be an absolute value bar, so you might see it either way. Doesn't really change much. So that's the one property a vector has. The second one is that almost all of them have a direction, except something we call the zero vector. Geometrically speaking, a zero vector is kind of just like a point. It has no length. So often we either think of it as having infinitely many directions or perhaps no direction, depending upon how you want to look at a specific situation. So except for the zero vector, every vector has a length and it has a direction. And so we're going to think of this in two different ways. We're going to look at this thing algebraically, and we're going to look at this thing geometrically. So what I've laid out here is kind of a geometric idea of how to think about vectors, a length and a direction, but there's also an algebraic way of putting it together. Namely, if we take a look at its x component and its y component. So we can also think of v as being the vector x0, y0, like this, where we have an x component, how far that vector is traveling in the x direction, and how far it's traveling in the y direction. And so we can think of vectors as having a length and a direction, or x and y components. Again, if we're dealing with three-dimensional vectors, it's possible that we do have a z component to it as well. And algebraically speaking, there's no reason why we have to stop at three components, although we lose the geometry a bit. If we go beyond three, you kind of lose the geometric aspects, but the algebraic aspects still work, even if you're going beyond 3 dimensions. So all vectors, kind of x, y, we say are in R2. The R stands for, that should be a familiar symbol for the real numbers. The superscript 2 here is just saying that there's two components. So we call that R2. So that would be if x and y are just any real numbers. Again, in this course, our focus will be on real numbers. If you're familiar with complex numbers, you could write it as the complex, the complex numbers squared. Again, x, y, z, that would be R3. And in general, we could go, again, we lose the geometry, but algebraically speaking, everything we're talking about would still work, and we could talk about Rn. So again, for geometric applications, we'll stick with the first two. But for some algebraic ideas and relationships, we can go to the last one. Do it for 4, for 5, for 20, for 80. The algebraic properties will still work even if we lose the geometric ones. All right. So We talked about the zero vector, so a zero vector would have nothing but zeros in its entries. So 0, 0, or 0, 0, 0 for an R3, etc. Those are the ones that have no length and no particular direction. So the question would be, how can we do some operations? How can we add? How can we subtract? How can we multiply? Can we divide? Full disclosure, we're not going to divide, but adding and subtracting, maybe multiplying by a number, kind of like we did for matrices. If the order of the course has this after matrices, very similar with matrices. We want to add them, we want to subtract them, we want to multiply them by numbers, we want to multiply them together. That one's going to be more complicated, you'll see in a future video. But the idea behind adding and subtracting, we'll start with adding because it's the easiest. Well, actually, let's start with scalar multiplication because it's the easiest one. If we want to do a scalar multiplication, if we're going to think of this, if we think of it geometrically, v, and if we want to multiply it by 2, if we multiply it by 2, we're going to double the length, but we're going to keep the direction the same. So same direction, twice as long. That's 2v. Or, if v is equal to x, y, z, then 2v would be, we're doubling the length in the x direction, doubling the length in the y. If it's an R3, doubling the length in the z. If we're in Rn, we just multiply everything by 2. But it doubles the length, but keeps the direction the same. If we wanted to do 3v, we triple the length. In general, algebraically speaking, we're just multiplying the length of each of these 3 components, which would keep the direction the same, at least for half of the values of k. So for which values of k are we not going to keep the directions the same? Well, feel free to pause the video and ask yourself, what values of k is the direction not going to stay the same? All right, so the first thing some people might be thinking of is if k is 0, then we're multiplying the length by 0, so now we've turned it into a 0 vector. So there is no direction, that's one thing. The other thing would be, what if k was negative? So if k is negative, instead of going a certain amount of units in the positive x direction, we would be going in the negative x direction, or vice versa. So if k is less than 0, then we take the absolute value of k times the length, but in the opposite direction. Again, geometrically speaking. So a positive k, we stay in the same direction. A negative k, we go in the opposite direction. So that's how we can multiply a vector by a scalar. Addition gets a little bit weirder, at least if you think of it geometrically. Addition-wise might not be quite as weird. So if v is, let's say, x1, y1, z1, and w is x2, y2, z2. And we want to add these things together. So here's v, and here's w. So if we're adding them together, let's pretend like the components are positive for just a second. If we're adding them together, we want to go x1 units. We want to go x1 units. And then we want to go x2 units a little bit more. Same thing for the y's. We want to go y1 units up and a certain amount of more units, whatever it was for the W. So we want to end up up here somewhere. And we can do that a little bit more geometrically by doing what we kind of call tip to tail. Namely, we're going to take a copy of W. Remember, a vector is all about the length and the direction, not where it starts, not necessarily where it finishes, just its length and its direction. We're going to take an exact copy of W and stick it to the end of V. We don't have to, but we could do the same thing with V. And what kind of shape have we created? Yeah, so the shape that we've created is a parallelogram. And V plus W is that vector right there. So geometrically speaking, this is how we can add them together. Algebraically speaking, it's a little bit easier. We're just going to add the components together. So adding algebraically is not particularly complicated. But the idea of what we're trying to do here eventually is, while looking at the components of this vector, adding together is easy to do algebraically. In terms of applications, or what we want to use it for, we want to use it for its geometry. So the geometry gives its usefulness. The algebra is what gives it an easier way of calculating. So that's why we want to do it both ways, because while we can do the algebra all day long for fun, I know everyone has fun doing some algebra, it's the geometry that gives us the applications, and that's what we're going to be using it for. So that's how we can add these things together. The last operation we'll talk about in this video is subtracting. So for subtracting, let's say we wanted to go V minus W. There's a couple ways of thinking about this. So let's take our same two vectors, looking geometry. I'll try and draw them the same. And personally, there are other ways of doing this. But personally, I like to just think of negative or subtracting W. Instead of thinking of it as subtracting, we can also think of it as adding the negative. In other words, I'm not going to take a W and put it at the end of V. I'm going to take a negative W. Same length, opposite direction. And I'm going to put that at the end of V. So V plus negative W, and then there it is, V minus W. Now, if we look at the above picture, that is, where it starts and finishes is not the same. In terms of length and direction, that would be the same thing as that one. So V minus W can also be thought as starting from the negative one, so starting from the one you're subtracting, from the end of W to the end of V. And that would give us the exact same thing as what we had right here. Again, it might be translated somewhere else, but the length is the same and the direction is the same, and that's the only thing that really matters. So two different ways of viewing the geometry behind subtraction. For the algebra, you just subtract the components, x1 minus x2, y1 minus y2, z1 minus z2. So once again, the algebra part of it is fairly easy. The geometry of what it stands for, what it represents, may be a bit more complicated, takes a few more examples to get used to, which I'm sure will be done in class. Right. And the last thing that we'll mention in this video is 2 points. So I've mentioned a vector is about length in the direction, not necessarily the initial point where it starts and the terminal point where it finishes. Well, what if that's what we're given? What if P0, actually let's use P, what if P and Q are just points in either 2 or 3 space? And again, honestly, it works even more, although you lose the geometry with it. So let's say we had point P right here and point Q over there. So let's stick with 2 dimensions. So there's a couple ways we can handle this. So let's say P was P1, P2, and Q is Q1, Q2 in terms of the actual point. So there's 2 ways we can handle this. The first way would be probably thinking like you might have in high school, which is, well, if we have P1 and Q1, what do we have to do to get from P to Q? And in the x direction, so we can write this as the vector PQ. In the x direction, that's Q1 minus P1. And how far we're going up would be Q2 minus P2. In other words, we can just subtract the components. So that's one way of thinking of it. Granted, another way we could think of it is instead of looking at the points, we could look at their vectors. So instead of thinking of this point, P, we could think of this vector starting from the origin. Same thing with Q. We can think of this vector starting from the origin, in which case PQ is just OQ minus OP, which would give us the exact same thing. So again, that might be overcomplicating the algebra, and it probably is. But in terms of the geometry, in terms of the applications, that's what we're really going to be using these vectors for once we get a handle on their properties and how we can compute with them. In terms of how we use them, these are the type of things we're going to be using them for. And one thing to note is the distinction between a vector and a point, there really isn't any. Okay. So this point could be, for example, 1, 1. But the point 1, 1 and the vector from 0, 0 to 1, 1 are effectively doing the exact same thing. So you'll notice the notation we use is using round brackets just like a point, which might seem fairly dangerous. But in practicality, the distinction between a vector and a point, there really isn't any. So it's not a big deal that we're using the same notation. All right. Again, these will all get reinforced, I'm sure, in your class and doing examples in class. But hopefully this just gives you an idea of some of the topics we're going to be seeing, at least at first, in an introduction to this vector. Okay, that's it for this video. See you in the next one.